Okay, today what I'm going to do is talk about the titration curve that we saw in that last video. Well, actually, the last two videos. I'm just going to talk a little bit about this curve. At the end of that, we saw that the pH went drastically up from 2.88 all the way up to 11.96, but it didn't do it in a linear fashion. It did it in this weird shaped curve. This weird curve comes from the fact that we create a buffer system. As soon as that strong base touches that weak acid, it creates a buffer, and that buffer is what maintains the pH at around this area. It keeps it about the pKa value of our weak acid. So whatever our weak acid's pKa is what's going to be very closely dominating that buffer system. And notice a dramatic spike here, that the pH goes up really quick at this point, because at that point we've lost our acid. Our buffer is destroyed, and our buffer, our weak acid is all gone. So at this point here, we no longer have acid in the solution as the base that is dominating everything, and at this point on, a curve pretty much is dominated by the strong base. So that's where that strange curve comes from. It comes from the fact that we create a buffer system, and then we see that the buffer gets destroyed, and as it gets destroyed, it doesn't take much to just go dramatically up to the top here to get a very high pH. And also note that at equivalence point, our pH is going to be greater than 7 when we have a weak acid titrated with a strong with a strong base, because we have that conjugate base of that weak acid left over. And if you need to check that out, go back and look at this point here to get that pH and understand why. Alright, so let's just briefly kind of look at the curve again and just kind of highlight some things on this. Alright, at the beginning, that initial point of the curve, what you have is just weak acid. So you cannot use the Henderson-Hasselbalch equation, because before we add any base to this titration, at the initial point, at point 0, what you have is just weak acid. You must use an ice table at that point. Now, any point right after that, as soon as you get past that, is where the buffer starts. So we get our buffer to start, and our buffer ends right before this part right here. So all along this point here and here, what you have is a buffer system. So that's why we have this flat part right here, is because of that buffer. And our buffer is going to be maintained close to that pKa value, which in this particular problem was 4.75. Alright, so that would be your halfway point. Now some things about that, remember I like to call this the halfway point. Now some things about that halfway point, don't forget that when you're at the halfway point, what you have is your pH is going to be equal to your pKa, which means your hydrogen concentration, if you undo the pH, is going to be equal to your Ka. And don't forget that the moles of the weak acid are equal to the moles of the conjugate base. That's all true at that halfway point. So keep that in mind when you get to that halfway point. Those are the things that are true for any weak acid strong base titration. Don't forget when you get to the equivalence point, what you have is hydrolysis of a salt, because your weak acid is all gone at this point. So you just have a hydrolysis of a salt. And anytime you have a weak acid titrated with a strong base, your pH is always going to be greater than 7. Okay? And then from this point on, up here, what you have is you have the strong base. The concentration of that hydroxide ion is going to dominate. You don't have to do anything but figure out how much of this is in excess. So find the excess amount of this left over, and then find the pH from that information, which you should know how to do. And that's why this curve is always the same. So if I were to come in and do another, I'll show you an example in just a second. Let me finish with this real quick. I think that's pretty much it for understanding the curve. One last thing is that I want to mention is that when you get to the equivalence point and beyond, no longer can you use the Henderson-Hasselbalch equation. Okay, you have to use ice tables here. Okay, so you have to use ice tables from here, and basically at that point is the last time we see equilibrium, because after that point there's no longer equilibrium. It's all dominated by the excess strong base. Now in between here and here, you can use that Henderson-Hasselbalch equation. Is valid anytime you have a buffer system. Okay, and notice what happens is when you're looking at that pH equals pKa plus log of the base over the acid. This is why I like this equation, because notice we're looking at how this changes. This is a constant. We're looking at how the pH changes as these two things change. As we go from this point to this point, the amount of the acid is going down and the amount of base is going up. And that's what's happening here. When we get to this point is when the base is equal to the acid. And at this point, so over here, your acid is going to be greater than your base. And on this side, my base is going to be greater than the acid. And that's kind of what's going on along this curve. And eventually, the acid's completely destroyed and the buffer is gone. Okay? So one thing I want to show you is a comparison of the strengths of acids. Let me show you that real quick. Okay, so what I have here are two different curves, and this one is looking at when we compare a strong acid to a weak acid titration. And then what you would have is your pKa, what we can look at is going to be right here. The halfway point is where your Ka is. So as an acid's Ka gets stronger, right, the acid gets stronger, it's going to have a higher and higher Ka. What that means is that we're going to drop lower and lower and lower and lower, so we see a bigger discrepancy between that top curve, which is represented by the strong base, and our strong acid. So if I were to do a strong acid, strong base titration, it would be the extreme case. And as the acid gets weaker and weaker and weaker, this portion rises higher and higher because my pH gets higher and higher and higher as I go through for those weak acids. So the point I wanted you to see here is that after the equivalence point, it's pretty much the same thing, because in all these titrations, the pOH or the OH concentration is going to dominate after the equivalence point is met, has been reached. Okay, so as our acid gets weaker, the curve gets higher and higher and higher and higher. So we can see there's a connection between the height of that curve, where that pKa falls, to where we would be. So this would be something like, pKa, we really wouldn't have pKa if it was a true strong acid, but you would have something like down here at like 2.0, where this could be something like 6.4. Okay, where it gets higher. So we can see that as we get up, we might have another one that would fall in here, and again, that one would be in between the strengths of these two acids. Okay, last thing I'm going to show you is the opposite curve. This is a weak base. I kind of changed the curve a little bit because I didn't have one that I wanted. A weak base titrated with a strong acid. I'm not going to go through all the calculations because, again, it's going to be another, it's pretty much the same pattern. But notice it's the inverse. I start with it being a base, and then I end with it being, no, I'm sorry, take that back. Gee, I'm starting down here. My fault. Starting up here with it being a base, and then we get that buffer system going, and then we end with an acid. So we end with the acid as opposed to starting with the acid. So it's the same thing. Notice the difference here. This is what I changed, is that the equivalence point for this particular reaction would be, because we're dealing with a weak base and the strong acid, our conjugate acid that would be left over at the equivalence point, the hydrolysis of the salt, would make the solution acidic. So whenever you have a weak base titrated with a strong acid, your pH is going to be acidic. Now if you had a strong base and a strong acid, then your pH would be 7. So for this one here, I would imagine that the equivalence point would be at that 7 mark, where the other ones wouldn't be. Okay, so hopefully that helps you with titrations, and I will talk to you guys later.